In this video, I'll be going through the 2022 mechanics paper. Question 1. A steel ball is held 40 centimeters above a table. The ball is released, and the time for it to fall to the table is measured. Calculate the time it takes for the ball to fall to the table. We'll start by writing what we have. We know the distance is 40 centimeters, or 0.4 meters. Our acceleration is the gravitational acceleration, negative 9.8 meters per second, since it's pointing downwards, and we'll define upwards as our positive direction. We know that the initial velocity is 0, and we're wanting to find the time. The kinematic equation with all of these values is this one here. Since our initial velocity is 0, this term here can be ignored. All we need to do now is solve this for t. We can do that by multiplying both sides by 2, dividing both sides by a, and then square rooting both sides and also swapping them around. Putting our numbers in, which gives me 0.29 seconds to two significant figures. The experiment was repeated with another ball of the same size, but half the mass. Ignoring any effects of air resistance, use physics principles to explain how the time for the second ball to fall compares to the time for the first ball to fall. As you should know, all objects experience the same gravitational acceleration of 9.8 meters per second. Ignoring air resistance, both balls will accelerate at this rate and land at the same time. The steel ball is now rolled along the table and off the edge as shown. The height of the table is 70 centimeters, and the ball hits the ground 1.8 meters past the edge of the table. Calculate the ball's final vertical velocity. What we have here is a projectile motion question, and in these questions we can analyze the horizontal and vertical motion as separate components. Focusing on the vertical motion, the initial vertical velocity is going to be 0, the final velocity is what we're trying to find, our distance is the height of the table, which is 70 centimeters or 0.7 meters, and our acceleration due to gravity is negative 9.8 meters per second. The equation with all of these values is this one here, where once again, because our VI is 0, we can ignore this term, giving us VF squared equals 2AD, which we can square root to solve. Putting our numbers in, where in this case I'm going to ignore our negative sign since we're only concerned about the magnitude, and because square roots don't like negative numbers, you would otherwise get a math error. Which gives me 3.7 meters per second to two significant figures. What assumption have you made? The main assumption we're making during projectile motion is that the only force acting is gravity, no air resistance. Calculate the size and direction of the velocity of the ball just before it hits the ground. You should start by showing that the horizontal velocity of the ball is 4.8 meters per second. To find the final velocity of the ball, we're going to use this equation here from Pythagoras, where we know our Vy, that is what we found over here, but we don't yet know our Vx, or at least we need to pretend we don't. It may be tempting to use this number and work backwards, but in doing so you will very rarely be awarded the full mark. Since we have no acceleration in our horizontal direction, the equation for Vx is just the distance divided by the time. And whereas we know our horizontal distance is 1.8 meters, we don't know the time, so we need to find that. Fortunately, the time in our x direction is going to be the same as the time in our y direction. So, given what we already know about the y direction, there are many ways that we could figure this out. I personally am going to choose this equation here, solving that for time by subtracting Vi from both sides, and now dividing both sides by a and swapping them around. As you might recall, our Vi is 0, our acceleration is 9.8, and our Vf is what we found earlier, is our 3.7. Putting those numbers in gives me 0.37755, which I'm going to leave unrounded since we're about to use it in another equation. You might wonder why I didn't use a negative 9.8, and I certainly could have done so, since our gravitational acceleration is pointing downwards, but so too as our final velocity, so I'd just be making both negative, and those negatives would just cancel out. Substituting for our time, I get 4.7676 meters per second, or rounding up we get our 4.8 meters per second, which is exactly what we're expecting. We can now substitute our Vx and our Vy into our final equation, which gives me 6.1 meters per second to two significant figures. Now we've found the size, but we haven't found the direction yet. To do that, we can consider our final velocity of 6.1 meters per second, consisting of a vertical velocity of 3.7 and a horizontal velocity of 4.8. Between our vertical and horizontal is a right angle, meaning that we can use SOHCAHTOA. Now, it hasn't precisely specified what angle it's looking for. However, as long as we're clear as to what our angle is, the mark should be awarded regardless. In this example, I'm going to find the angle to the vertical, but you would be just as right to find the angle to the horizontal. Now, we could use any of the trigonometric relationships. Out of no particular preference, I'm going to use the sine relationship, where we know that sine of the angle is the opposite over hypotenuse, where our opposite is our 4.8 and our hypotenuse is our 6.1. Taking the inverse sine of both sides to solve for our angle, giving me 52 degrees to two significant figures. Question 2. Two carts are set up with a spring between them. The spring is compressed by 10 centimeters. When the spring is released, the carts rapidly move apart in opposite directions. The spring has a spring constant of 250 newtons per meter. Calculate the total energy released from the spring. The equation for the energy in a spring is this one here, where we know our K is 250 and our X, which is our displacement, is 10 centimeters or 0.1 meters, giving me 1.25 joules. The mass of the red cart is 0.5 kilograms, and the mass of the blue cart is 2 kilograms. The final velocity of the blue cart is 0.5 meters per second. Calculate the final velocity of the red cart. The concept we have to use is conservation of momentum. Assuming our carts are stationary initially, we know our initial momentum must be equal to 0, and because of conservation of momentum, in the absence of external forces, we know that the final momentum must be 0 as well. And so our final momentum is 0 and is comprised of the momentum of our red cart and the momentum of our blue cart. Because momentum is mass times velocity, we can make those substitutions, where the mass of our red cart is our 0.5 kilograms, mass of the blue cart is 2, the final velocity of our blue cart is 0.5, and the velocity of our red cart is what we're trying to find. Our next step is therefore to solve this equation for VR, subtracting MB/VB from both sides and swapping the sides around, dividing both sides by MR, and now putting our numbers in, giving me negative 2 meters per second, where the negative indicates that our velocity of our red car is in the opposite direction to the positive velocity of our blue car. What assumption, if any, have you made? Momentum is conserved, assuming there are no external forces. In a different experiment, the red and blue carts are set moving in opposite directions with equal momentum. The blue cart is stopped at the end of the track by a solid board, and the red cart is stopped by a padded wall. Use physics principles to explain whether the blue cart or the red cart will suffer the most damage as they both stop. Our blue cart, being stopped by a solid board, is going to be stopped suddenly, so our stopping duration is going to be low. Whereas our red cart, which is being stopped by a padded wall, will take longer to stop due to this cushioning, which means that our duration is going to be high. Knowing that our force is equal to our change in momentum divided by the duration over which it changed, assuming there is equal momentum as we are told to do so here, a lower duration is going to result in a higher force, and vice versa. The blue car experiences a shorter stopping duration than the red car, because the momentum change is the same in each case, and F equals delta P over delta T, the blue car will experience a larger force than the red. The blue car will therefore suffer more damage. The 2 kilogram blue cart, moving at 2 meters per second, took 0.02 seconds to stop when it collided with the solid board. State Newton's third law of forces in the context of the collision of the blue cart and the solid board. Newton's third law is that every force is accompanied by an equal and opposite force. So in the context of this situation, the force applied by the board onto the cart is equal and opposite to the force applied by the cart onto the board. Calculate the size and direction of the average force experienced by the solid board during this impact. Whenever we're given a duration for a collision to occur, chances are we're going to be looking at impulse. The relevant equation is the one we've used above, that the force is equal to the change in momentum divided by the duration over which it changed. We're given the duration over which it changed, and we know that the change in momentum is just going to be our mass times velocity, which is our 2 kilograms multiplied by our 2 meters per second, giving us 4 kilogram meters per second. Putting those numbers in gives me 200 newtons. And so we have found the size, but we still need to state the direction. As far as I can see, we're given no indication as to which direction the blue cart is travelling, and so the best we can do is to say that the force experienced by the solid board is going to be in the direction that the blue cart is travelling. Question 3. Calculate the spring constant for a spring that extends 200 mm when a 2.94 Newton weight is hung on it. Our extension, which is our 200 mm, converted to meters, is 0.2 meters. The equation for the extension of a spring is force equals negative kx, where, because we're only interested in the magnitude, we can forget the negative. Solving this for our spring constant by dividing both sides by x, putting our numbers in, gives me 14.7 newtons per meter. A block is attached to 2 identical springs and hung from the ceiling. On the diagram below, add labelled arrows to show all the forces acting on the block. First of all, we have the gravitational force, and we have our 2 tension forces from the springs. Draw a labelled vector diagram to show how the 3 forces acting on the block add together. Because our block isn't moving, we know that the sum of all of our vectors, where I'll call this spring 1 and this spring 2, must equal 0. So we should be able to chain them together and end up where we started. So our downwards force of gravity is going to equal our Fs2 plus our Fs1. An athlete in training holds a uniform rod 2 meters long, stationary in a horizontal position. The mass of the rod is 3 kilograms. Calculate the forces Fa and Fb that are required by the athlete's hand to hold the rod in equilibrium in the horizontal position. For this, we need to know all the forces. We have the force from this hand and the force from this hand, but we also have the weight of the rod. Because the rod is uniform, we can assume that it acts from the middle. Knowing that the rod is in equilibrium, we know that the torques must be balanced. So if we choose our Fa as our pivot, we know that the torque produced by Fb must be equal to the torque produced by Fg. Because torque is just force times distance, and the distance for our Fb from our pivot of Fa is 0.3 meters, and for Fg it is just 1 meter, half the length of the rod. So we can replace our torque of B with 0.3 Fb, and our torque from our gravitational force as just 1 times Fg, or just Fg. Dividing both sides by 0.3, and knowing that our Fg is going to be our mass times gravity, which is going to be our 3 kilograms, multiplied by 9.8, we can make that substitution, giving me 98 newtons. Now to find our Fa, we could make our pivot Fb and calculate the torques from there. However, there is a quicker way. What we also know is that the forces must be balanced. More specifically, that our up forces, which is just our Fb, must be equal to our down forces, which is our Fa plus our Fg. Subtracting Fg from both sides and swapping our sides around, putting our numbers in, gives me 68.6 newtons. Now the question hasn't specifically asked for direction, and you would think that it is somewhat obvious from the diagrams, but it also can't hurt. A jelly is placed on the edge of a plate, and the plate starts to spin, so the jelly is moving in a circle. As the plate speed increases, the jelly initially maintains its position at the edge of the plate until it eventually slides off. Use physics principles to explain why the jelly initially stays on the plate, but as the speed increases it slides off. Your answer should include naming of any relevant forces involved, how increasing the velocity affects the situation, and a description of the path the jelly would take when it first slides off. So we of course have a centripetal motion problem where we have the centripetal force being provided by the force of friction. The centripetal force is equal to the mass times velocity squared over r, and so as our velocity increases, eventually it reaches a point that exceeds the force that the friction can provide. As the jelly slides off the plate and the friction force no longer acts, the jelly is going to move in the direction of its tangential velocity. So let's write that down. The jelly experiences a centripetal force provided by the friction with the plate. As the plate speed increases, it eventually reaches a point where the centripetal force required exceeds what the friction can provide. When the jelly slides off the plate, it no longer experiences the friction centripetal force and moves in the direction of its tangential velocity. And we're done.